I'm Mikayla, and I'm pre-PA here at Tennessee Tech.
I'm Isaac Reff, and I'm a senior chemical engineer.
I'm Josh Berry. I'm a chemical engineering major.
And,
Sorry. I'm Ben. I'm a pre-med.
and we are mitigating ventilator-associated pneumonia, or VAP, with a new endotracheal tube design. So our journey started at Cookeville Regional Medical Center, and we were able to meet with a respiratory therapist, which is where we learned more about ventilators and managing patients on ventilators. And so during our 4 visits, we began to notice how many patients are on ventilator machines in the hospital. And so we were able to ask one of the nurses, what is the biggest problem when you are managing these patients? And she said the biggest risk when somebody is on ventilation is VAP. And so that kind of presented its opportunity, and we did more research. And we learned that the longer patients are on a ventilator, the more likely they are to develop VAP. We also found out that 86% of nosocomial diseases, which is just a disease the patient gets while they're at the hospital, is associated with VAP. There are approximately 300,000 cases a year just in the United States, and the mortality rate is approaching 50%. So that's high numbers. Also, the duration of that patient's hospitalization increases by 7 days, and the increase of the healthcare cost is $40,000 per patient. So enough numbers to stimulate us to pursue this route.
So how VAP is caused is basically oronasal secretions are generated in the mouth and nasal passages, and those can pull up around the cuff on the endotracheal tube. The endotracheal tube would be inserted into the trachea, and a syringe would be used to inflate the cuff to kind of create the best seal it can.
So the thinking that our group went through is if the purpose of the endotracheal tube cuff is to seal off the trachea and sort of try and prevent those secretions from reaching the lungs causing VAP, then obviously the cuffs aren't working to their full potential. So we set out to redesign the endotracheal tube cuff specifically. In order to properly do this, we decided we had to answer a few questions first, those being what current models exist, what current models are being used in the hospital, what are on market that we just haven't seen before because hospitals haven't bought them. And then what are the issues associated with these current designs? Why are these designs not working? Why are people still getting VAP with all these new designs with endotracheal tube cuffs? So we did some preliminary research, and that gave 2 major problems with the majority of the cuffs that we found. These were first microchannel formation, which is basically the formation of small tunnels between the inflated cuff and the wall of the trachea, where secretions are able to bypass the cuff and enter into the lungs, causing ventilator-associated pneumonia. And the second one being the pulling of secretions on top of the cuff, where then secretions can then enter the lungs through these microchannels, or when you deflate the cuff, they simply just fall into the lungs. So after considering all the research that we have looked into, our group came up with 4 different design ideas, all with the goal of redesigning the endotracheal tube cuff and ultimately reducing the incidence of VAP.
The first of those designs is the ribbed cuff design. The trachea is naturally ribbed, so we kind of went from there. The first thing that came to mind in our brainstorming session was having a ribbed cuff just like this, and then when we did a patent search, we found basically the same thing, which this drawing is from. And this actually minimizes the contact surface and reduces sore throat and ischemic damage after they're weaned off the vent.
Our second invention idea was the double cuff, and basically the 2 cuffs would protect the larynx and the trachea from the secretion from the oronasal route, and then also the esophageal route. And basically the idea here is 2 is better than 1, and we went and met with our anatomy and physiology professor here at Tennessee Tech, and he told us as long as we could visualize and make sure that the cuff was in the correct place, that it would be quite possible to do this double cuff idea. So then we went to the sim lab and we contacted Carrie Cass, the lab coordinator, and tried to get a good visual with the laryngoscope on one of the mannequins in the sim lab, but we were unable to get a good view to see it. And then the next thing that happened, we found a patent for basically the exact same design, so that one was out as well.
Our third design that we thought of was a mechanical cuff design, and basically the thinking behind this was, what if we replaced the pressurized mechanism, as most cuffs are inflated with water or air, with a mechanical one. We consulted with Dr. Pardue, who offered some great ideas, and the initial thought was to sort of make some sort of structure like a vascular stent, which is what these diagrams are from. Most vascular stents that I've seen at least are metal, so we would want to find something a little softer, maybe some sort of polymer. Dr. Pardue was kind enough to print us some of those. And the key of this would have to be rigid enough that it could properly seal the airway, but soft enough that it wouldn't do any damage to the trachea. And then finally, there was the problem of actually removing the cuff, because most stents aren't removed from the body once they're placed. And Dr. Pardue again offered the thought of a vacuum seal around the cuff to where when a vacuum is applied, it would collapse for removal.
And this leaves us with our final invention idea, the most novel of the four, the laser topographical 3D printed ETT cuff. And ignoring the fact that this looks like a glorified fidget spinner, it's actually a highly sophisticated 3D laser imaging device that's currently being used in dental applications. They're used to make 3D models of people's mouths and then 3D print the molds to see how well they fit and how comfortable they are. And so the idea is to adapt existing technology just to move from the mouth down to the throat to construct, using the laser imaging, a 3D topographical map of the inside of each patient's throat, and then using this highly precise, highly customized data, use software, and then 3D print it. Obviously, this would be used for patients that are intubated over a longer period. If you're going to only be on a vent for 2 or 3 days, you probably won't get one of these, but we often see patients on them for months or years at a time. So having something very precise and very customizable could potentially be very useful. And this idea could actually be used with any of our other 3 ideas. You could have a custom-built ribbed ETT cuff or double cuff. So next step, like I just said, really any of these ideas are viable. What needs to happen next is just more development, research, funding, and testing. And as time would go on, a clear competitor would stand out among the rest. We would pick one, sort of finalize, this is the idea that we think is the best, continue to test and refine, eventually end up patenting it and then moving on to commercialization. VAP is a serious and complex problem that has been confounding the medical field for about 40 years. Most of the patents we found and articles that were written have come from the 70s, and we're still seeing a really high mortality rate, extended stays in the hospital, even though we've been attempting to solve this problem for over 40 years. And one of our theories is that the technology that we have now simply didn't exist 40 years ago. And so when we first approached this problem, the tech that we have now is light years ahead of what we had back in the 70s. And so our designs are incorporating modern technology with the years of research that have been going on since the 70s. So our goal ultimately is to prevent 100% of VAP cases, but even a 10% reduction is significant and will save thousands of people's lives and hundreds of thousands of dollars. So, thank you. Any questions?